Assalamu alaikum students. In this lecture, we will discuss the voltage regulation and efficiency of a transformer. There are two important topics. The first one is the voltage regulation of a transformer, and the second one is efficiency of a transformer. So first of all, we will discuss the voltage regulation of a transformer. Now the question is, what is the voltage regulation of a transformer? Voltage regulation is basically defined as the change in magnitude of the secondary voltage of a transformer when the load changes from no load to full load, assuming a constant primary voltage. It means voltage regulation is basically the change in magnitude of the secondary voltage instead of primary voltage. So this is the important point. Voltage regulation is not the change in primary voltage. It is basically the change in magnitude of the secondary voltage when the load changes from no load to full load. So this is the definition of the voltage regulation of a transformer. Voltage regulation is basically tell us how well the transformer can maintain the output voltage. The output voltage of the transformer is the secondary voltage, because the input of the transformer is basically connected with the primary side and the output of the transformer or load is connected across the secondary side of the transformer. So the voltage across the secondary circuit is called the output voltage. The voltage across the primary circuit is called the input voltage. So voltage regulation is basically tell us how well the transformer can maintain the output voltage, as the magnitude and power factor of the load varies from no load to full load. Voltage regulation is defined based on the output parameters. In case of transformer, the output is secondary voltage. That's why we define the voltage regulation based on the secondary voltage. So this is the important point of the voltage regulation of a transformer. So the approximate equivalent circuit referred to the secondary side is shown here. As you can see in this circuit, this is the secondary voltage and this is the secondary current, and this is the R equivalent resistance with respect to the secondary side, and this is the X equivalent referred to the secondary side. This is the excitation branch elements, that is RC and XN. This circuit of the transformer is basically referred to the secondary side of the transformer. As we have already discussed, we can convert the circuit from primary to secondary or secondary to primary. So this equivalent circuit is basically referred to the secondary side because the voltage regulation is basically the change in magnitude of secondary voltage, not the primary voltage. So that's why we transform the circuit from primary to secondary. And R equivalent here is equal to Rp over A square plus Rs. Rs means secondary winding resistance, Rp means primary winding resistance, A means the turn ratio. Turn ratio is basically A is equal to Np over Ns or Vp over Vs. X equivalent is equal to xp over A square plus xs. This is the primary reactance due to leakage flux, and this is the secondary reactance due to leakage flux. As we have already discussed, when we convert or when we transform primary resistance or reactance into secondary side, then we will divide the A square. So that's why we have divided here primary elements with A square. So this is the approximate equivalent circuit of a transformer referred to the secondary side. So in case of no load condition, the current will be zero. That is, the value of the current, that is secondary current, will be zero. Because when there will be no load connect, then the circuit will be open. When the circuit will be open, then the value of the current will be zero. So that's why in case of no load condition, the current, that is the secondary current, will be zero. When we will connect the load across the secondary side of the transformer, as we have already discussed, we connect the secondary side of the transformer with load and primary side of the transformer with the power supply. So when we will connect the load across the secondary side of the transformer, then the secondary voltage will drop. As we know, in case of inductive or resistive load, voltage drops. When the load will increase, then the voltage drop will be more. So the formula of the voltage regulation of a transformer is VR is equal to secondary voltage at no load condition minus secondary voltage at full load condition divided by secondary voltage at full load multiplied by 100. It means when there will be no load, then the secondary voltage will be maximum. So this is the secondary voltage at no load. When we will connect the load, then the voltage will drop. That is, in case of inductive or capacitive, or in case of inductive and resistive load, voltage will drop. So this is the secondary full load voltage when we will connect the load. So this is the voltage regulation formula. By using this formula, we can calculate the voltage regulation of any transformer. As we have already discussed, the voltage regulation is basically defined based on the output parameters. In case of transformer, the output is secondary. So that's why we defined the voltage regulation based on the secondary voltages. There is no primary voltage. These are the secondary voltages. So as we know, in case of no load, as we know, primary voltage divided by secondary voltage is equal to A. A means turn ratio. A is basically equal to NP over NS or VP over VS. So in case of no load, VP over VS will be equal to A. These values are in case of no load. After the cross multiplication, the value of the secondary voltage will be equal to VP over A. This is the secondary voltage at no load condition. So putting the value of secondary voltage at no load in this equation, we will get voltage regulation is equal to VP over A. As we know, V secondary at no load is equal to VP over A. So putting the value of secondary voltage at no load is equal to primary voltage divided by A into this equation, we get voltage regulation is equal to VP over A minus Vs full load divided by V secondary full load multiplied by 100. So in case of per unit system, So in the per unit system, we can define the voltage regulation. In the per unit system, the formula of the voltage regulation will be equal to V secondary no load voltage in per unit minus secondary voltage at full load condition in per unit divided by secondary voltage at full load in per unit multiplied by 100. So this is the voltage regulation formula in the per unit system. It means in per unit system we can calculate the voltage regulation of a transformer as well. Now the question is, how will we calculate the voltage regulation of the transformer? As the approximate equivalent circuit of the transformer refer to the secondary side is shown here. As we have already discussed, in this equivalent circuit, the effect of excitation branch, this is the excitation branch, that is RC over A square, magnetization reactance divided by A square, this is the excitation branch. The effect of excitation branch can be ignored. As we have already discussed, in this equivalent circuit, the effect of excitation branch can be ignored for simplicity. So, thus if the effect of excitation branch ignored, then the simplified equivalent circuit will be look like this. So in this circuit, we ignore the effect of excitation branch, then the equivalent circuit of the transformer in simplified form will be look like this. So this is the equivalent circuit of the transformer in simplified form. So to find the voltage regulation of a transformer, it is necessary to understand voltage drops within it. So voltage regulation is basically depends on the voltage. To calculate the voltage regulation of the transformer, so it is necessary to understand the voltage drops within it. So the voltage regulation of the transformer depends on two parameters. As you can see in this simplified equivalent circuit, the first one is magnitude of series impedances. These are the series impedances. So voltage regulation is basically depends on the magnitude of series impedances. And the second one is phase angle of the current. So this is the current. Voltage regulation is basically depends on the phase angle of the current. And the second one is the magnitude of series impedances. So voltage regulation can be calculated. So can be calculated if we calculate the effect of series impedances and the phase angle of the current. So these two are the important parameters. So the easiest ways to determine the voltage regulation. So first of all, we will determine the effect of magnitude of series impedances and the phase angle of the current. So to calculate these two parameters, the easiest way to determine the effect of series impedances and the phase angle of the current is to examine the phasor diagram. So first of all, we will discuss the phasor diagram, then we can calculate the voltage regulation of a transformer. So to check the effect of these two parameters, we will examine the phasor diagram of a transformer. So first of all, we will determine the equation of primary voltage from this equivalent circuit by applying the KVL. This is the simply series circuit. By applying the Kirchhoff voltage law, we get Vp over A minus Vs, because the polarity of Vs is opposite to the polarity of Vp over A. So that's why the sign of Vs in this equation will be minus. And then the minus Is into R equivalent S, because in case of series circuit, the current will be same, that is Is will be equal to A into Ip. So that's why R equivalent into Is minus Is into Jx equivalent is equal to 0. So this is the equation we obtain from this equivalent circuit by applying the Kirchhoff voltage law. If we will take these three parameters to the other side of the equation, that is to the right side of the equation, then we will get Vp over A is equal to Vs plus R equivalent into Is plus Jx equivalent into Is. So this is the equation of the voltage, that is the Vp over A. So let us assume the angle of secondary voltage is 0 degree and the angle of the current will depend on the load, that is the angle of secondary current will depend on the load. For reference point, let we assume the angle of secondary voltage is 0 degree and the second parameter is the current. The angle of the current will depend on the load. So there are three different types of the load. The first one is the inductive load. In case of inductive load, current lags the voltage by 90 degree. If the current is lagging, then the power factor will be lagging as well. So that's why in case of inductive load, power factor will be lagging. In case of resistive load, the voltage and current are in phase. That is, the phase difference between voltage and current is 0 degree. So that's why in case of resistive load, the power factor will be unity. That is, the value of the power factor will be 1. And in case of capacitive load, in case of capacitor, current leads the voltage by 90 degree. So if the current will lead, then the power factor will be leading as well. So that's why in case of capacitive load, power factor will be leading. It means in case of inductive load, power factor will be lagging. Then in case of unity in resistive load, power factor will be unity, and in case of capacitive load, power factor will be leading. So first of all, we will discuss the phasor diagram of a transformer operating at a lagging power factor. Then we will discuss the phasor diagram of the transformer operating at unity power factor. After this, we will discuss the phasor diagram of a transformer at leading power factor. So first of all, we will discuss the phasor diagram of a transformer at lagging power factor. As we have already discussed, in case of inductive load, current lags the voltage. So if the angle of the voltage is 0 degree, then the angle of the current will be in minus. The reason is that in case lags mean the angle of the current will be less than the angle of the voltage. So that's why let's assume the angle of secondary voltage is V angle of 0 degree for reference point. So this is the reference value. We assume that the angle of secondary voltage is 0 degree. It means the angle of the current will be in minus. The reason is that because current lags the voltage. Lagging means the angle of the current will be less than the angle of the voltage. So the angle of the voltage is 0 degree. So less than the 0, it means the angle of the current will be in minus. As we know, the equation of the equivalent circuit, as we have already discussed, Vp over A is equal to Vs plus R equivalent into Is plus Jx equivalent into Is. So, as we know, the angle of secondary voltage, we assume that is 0 degree. So first of all, we will draw the secondary voltage. So this is the secondary voltage. As we know, in the x-axis, the angle is 0 degree. So that's why we draw the secondary voltage at x-axis. So this is the secondary voltage. So in case of inductive load, as we have already discussed, current lags. It means the angle of the current will be in minus. So that's why this is the angle of the current, that is the Is. Because the angle of the current will be less than the 0. As we have already discussed, in case of inductive load, current lags the voltage. So that's why the angle of the current will be in minus sign. So this is the current Is. After this, we will draw the R equivalent into Is. As we know, the angle of current is minus theta and the angle of the resistance is 0 degree. When we will add, because these two factors are multiplied with each other, the angle of the current is minus theta and the angle of the resistance is 0 degree. When we will multiply it R into I, then the angle will be add up. So that's why the angle of the R into I will be in minus as well, because the angle of the R is 0 degree and the angle of the current is minus theta, because the lagging load. In case of inductive load, current lags, so that's why the angle of the current is minus theta. When we will multiply it R into I, then the angle will be add up. So when we will add minus theta into 0, the overall angle will be minus theta. It means the overall angle of this factor in the minus as well. So that's why this factor will be look like we will draw in this direction. The reason is that the overall angle of this factor is minus theta. So that's why we will draw the vector of R equivalent into Is like this. Now, the last parameter is Jx equivalent into Is. As we know, the angle of the current is minus theta due to inductive load and the J means angle of 90 degree. J is basically equal to 1 angle of 90 degree. So when we will add 90 degree in minus theta, it means in this case we will add the 90 degree in minus theta. So if we will add the angle 90 degree in minus theta, so the vector will be like this. Jx equivalent Is will be like this. So this is the 90 degree. 90 degree means J is basically equal to 1 angle of 90 degree. So that's why this factor, the vector of this factor, that is Jx equivalent Is will be like this. Because when we will add minus theta with 90 degree, the overall effect will be look like this. So the resultant of all the, that is the sum of all three, will be equal to Vp over A. So this is the first element Vs, this is the second element R equivalent into Is, and this is the third element Jx equivalent into Is. And the sum of all these three will be equal to Vp over A. So this is the resulting Vp over A, sum of all these three. Now, as you can see in this phasor diagram, as we know, voltage regulation is equal to Vp over A minus V secondary at full load divided by secondary voltage at full load into 100. So in case of no load, this is the no load secondary voltage. So when we will connect the load, so this is the secondary voltage at full load condition. As you can see in this diagram, this is the no load voltage As you can see in this is the voltage Vs, and the resulting voltage Vp over A is basically greater than the Vs. From this phasor diagram you can conclude the no load voltage is greater than the full load voltage, that is Vp over A is greater than the Vs. So if from this phasor diagram you can compare these two voltages. This is the greater than, that is Vp over A is greater than the secondary voltage. So that's why when this value will be greater than this value, this is the full load voltage at secondary voltage. When this voltage will be greater than this voltage, then the answer of the voltage regulation will be positive. So we can say that positive voltage regulation. Positive voltage regulation is basically tell us at no load the voltage will be maximum or voltage will be more. When we will connect the load, then the voltage will drop. So if the voltage, when the voltage will drop, then the voltage regulation will be positive. So if the voltage regulation is positive, we can conclude it means the load is inductive load or lagging power factor. So now we will discuss the second type of the load, that is resistive load. As we know, in case of resistive load, the current and voltage are in phase. That is, the power factor will be unity power factor. So similarly, let assume that the angle of secondary voltage is equal to V angle of 0 degree. As we have already discussed, the equation of Vp over A is equal to Vs plus R equivalent into Is plus Jx equivalent into Is. So first of all we will draw the vector of Vs at 0 degree. So this is the vector of Vs. Then we will draw the R equivalent into Is. As we know, in case of resistive load, current and voltages are in phase. That is, the angle of the current and the voltage will be same. Same angle means if the angle of the voltage is 0 degree, then the angle of the current will be 0 degree as well. If the angle of the voltage is 90 degree, then the angle of the current will be 90 degree as well. In case of resistive load, voltage and current are in phase. So now the angle of the voltage is 0 degree. So that's why the angle of the current will be 0 degree as well. So this is the angle of the current Is. As we know, the angle of the resistance is 0 degree and the angle of the current is 0 degree as well in case of resistive load. So when we will multiply these two angles, 0 plus 0, the answer will be 0 degree. So that's why R equivalent into Is will be in the x-axis as well. So this is the R equivalent into Is. And then the third factor is Jx equivalent into Is. So J means 90 degree. It means we will add 90 degree in plus the angle of the current is 0 degree. When we will add 90 degree in 0, then the vector will be like this. So this is the Jx equivalent into Is. So overall resultant will be the sum of all these three, that the resultant is Vp over A. So this is the resulting Vp over A. Now, as you can see in this diagram, this is the voltage Vs and the resulting voltage Vp over A is greater than the Vs. So that's why if the value of the Vp over A is greater than V over Vs, as we have already discussed, in case of resistive load, Vp over A is greater than Vs as well. So if the voltage of Vp over A is greater than the Vs, then the voltage regulation will be positive as well. So that's why the voltage regulation in case of resistive load will be positive as well, because in case of resistive load, no load voltage is greater than the full load voltage. But as compared to inductive load, this is the less greater than. So that's why in case of inductive load, voltage regulation is positive, and in case of resistive load, the voltage regulation will be positive as well. But in case of resistive load, voltage drop is less as compared to the inductive load. So now we will discuss the third type of the load, that is the capacitive load. In case of capacitive load, current leads the voltage. When the current will lead, then the power factor will be leading as well. So similarly, let's assume the angle of secondary voltage is equal to V angle of 0 degree. So as we know, Vp over A is equal to Vs plus R equivalent into Is plus Jx equivalent into Is. The phasor diagram is, so first of all, we will draw the Vs at 0 degree. So this is the Vs. In case of capacitive load, current leads. Leading means the angle of the current will be more than the angle of the voltage. So the angle of the voltage is 0 degree. It means current is leading. It means the angle of the current will be greater than the 0 degree. So that's why the angle of the current will be greater than the 0 degree. So this is the vector of current Is. So next one is the R equivalent into Is. As we know, the angle of the resistance is 0 degree and the angle of the current is greater than 0. When we will add 0 plus theta, then the overall angle will be greater than 0. So we will add Vs with R equivalent into Is. We start the R equivalent into Is from vector from this point because these three all are adding. So that's why where the Vs will end, then we will start the next, that is R into Is. So this is the vector of R equivalent into Is. This is the greater than the 0. The reason is that current is leading. When the current will lead, then the angle of the current will be greater than the voltage angle. So the third parameter is Jx equivalent into Is. The angle of the current is positive and J means 90 degree. So we will add 90 degree here. So this is the vector of Jx equivalent into Is. So this is the resulting Vp over A, that is all the sums of, that is the resulting of Vs plus R equivalent Is plus Jx equivalent Is is Vp over A. So this is the Vp over A. Now as you can see in this figure, the voltage Vs is greater than the voltage Vp over A. The voltage Vp over A is less than the voltage Vs. So if Vp over A is less than the Vs, Vs means full load voltage, Vp over A means no load voltage. So now the no load voltage is less than the full load voltage in case of capacitive load. So when this factor will be less than and this factor will be greater, when this factor will be greater, the overall answer will be in minus. So that's why in case of capacitive load, voltage regulation will be negative. So if the voltage regulation is negative, it means the load is capacitive load. If the voltage regulation is positive, it means the load is inductive or resistive load. So based on voltage regulation, we can find out which type of the load is, that is inductive load, capacitive load or resistive load. So now we will discuss the efficiency of a transformer. The efficiency of the transformer is the output power divided by the input power multiplied by 100. We represent the efficiency with eta. The formula of the efficiency is output power over input power into 100. As we know, input power is basically equal to output power plus losses. So put the value of input power in this equation, we will get eta will be equal to, that is efficiency will be equal to output power over output plus losses into 100. Because as we know, input power is basically equal to output power plus losses. So as we know, in case of transformer, there are three types of the losses. The first one is the copper losses, and the second one is hysteresis losses. The third one is eddy current losses. The combination of eddy current and hysteresis losses is called the core or iron losses. The losses I square R is called the copper losses. Now, as you can see in this equation, the relationship between losses and efficiency is inversely proportional. It means when the losses of the transformer will increase, then the efficiency of the transformer will decrease. So, because the relationship between losses and efficiency is inversely proportional. If the losses is minimum, then the efficiency of the transformer will be maximum. So the losses is basically depends on three parameters, that is copper losses, hysteresis losses and eddy current losses. So main losses are copper losses and the core or iron losses. As we know, the combination of hysteresis and eddy current losses is called core or iron losses. So we represent the copper losses, P copper, we represent the core or iron losses with P core, and this is the output power, P out. We just put the value of losses, that is losses in the transformer are core losses and copper losses. So therefore the formula efficiency is now output power divided by output power plus losses, that is plus core losses plus copper losses. It means we can calculate the efficiency of the transformer if we calculate the copper and core losses of the transformer. The copper and core losses of the transformer we can calculate by performing the open circuit test and the short circuit test. As we have already discussed, in case of open circuit test, we basically find the core losses of the transformer. In case of short circuit test, we find the copper losses of the transformer. So these two losses we can calculate by performing the open and short circuit test of the transformer. So it means if we want to calculate the efficiency of the transformer, so first of all we will perform the open circuit test and the short circuit test to calculate the core losses and the copper losses. So this is the transformer and this is the load. As we know, we connect the load at the secondary side of the transformer. Let the voltage across the load is Vs and the current flowing through the load is Is. So this is the cos theta power factor of the load. So output power will be equal to Vs, the voltage across the load, into Is, the current across the load, into the power factor, that is cos theta. Theta is basically the phase difference between voltage and current. As we know, in case of resistive load, the phase difference between voltage and current is 0 degree. In case of capacitive and inductive load, the phase difference between voltage and current is 90 degree if we apply pure inductive or capacitive load. If we apply the combination of inductive, capacitive and resistive load, then the phase difference can be between 0 and 90 degree. So if we put the value of output power is equal to Vs into Is cos theta in this equation, then the formula efficiency will be like this. So eta will be equal to, that is efficiency will be equal to Vs into Is cos theta divided by Vs Is cos theta plus copper losses plus core losses into 100. We just put the output power is equal to Vs Is cos theta in this equation. So that's why formula of the efficiency is now Vs into Is over cos theta divided by Vs Is cos theta plus copper losses plus core losses multiplied by 100. So by using this formula, we can calculate the efficiency of the transformer. So this is the formula to calculate the efficiency of a transformer. So that's it for this lecture. So in next lecture, we will solve a numerical problem to further clear the concept of theory.